Thank you, Peter, for the kind words. And thank you, Nick, for the very good scientific introduction to my presentation, which is a bit more down-to-earth engineering development of the tool. So hMRI Toolbox is what was used to reconstruct some of the maps that Nick presented you. But it actually started quite a while ago, about 17 years ago. That was called the voxel-based quantification. So the idea was that we wanted to get the quantity at each voxel, not the quality of the tissues. And looking back at the code, I found that earliest bit dates from 2008 by Chloe, who will be around later on today, I believe. And then it was really used for the first time in, as far as I know, by Bogdan Dragansky for his publication in 2011. Then Martina published that in famous aging and qMRI data paper in 2014. And that's something where things started being a bit more professional, and the code was versioned on the in-house SVM server. And then there were a bunch of people involved based on the names found in the code. You see Nick is there, John, Bogdan, Gunter Helms, Chloe Ferrat, who just arrived, Antoine, who's not arrived. Then we at some point, I remember why, I think Nick initiated the switch to VB2 to hMRI, probably associated to one of the grants you obtained, I think. And we really publicly released the tool in 2018 and got a few papers on that. And as far as I know, the latest release is from 2023. And we also switched from local SVM to GitHub. So the code, everything now is done through GitHub. And we had a bunch of other contributors. And at last, Martina's name appears among the contributors. So that's the overall framework. That's from the paper presenting the tool. And the key thing is, we take the data that's on the left, then we do lots of processing in the toolbox in order to arrive to those biomarkers, volumetry, myelin, iron that Nick was talking about. And some of it relies on SPM, but there are a few original bits, and that's mainly the map creations. That's really the heart of the tool, and that's what Nick was talking about. And so you acquire a set of images, like 20 or so high resolution anatomical images with specific parameters, plus bias fields and field maps and so on, in order to create our quantitative maps. So that's pretty much solving those equations, and the end results are highlighted here in red. So that's the R1, R2 relaxation parameters, proton density, and magnetization transfer. The key thing I want to highlight, and that's from the engineer's perspective or software perspective, is these rely on some specific parameters. So each image has to be acquired with a different TE, so eco time, or some specific flip angles for the field maps. And that means that, and then we also need to model those B1 maps, the emission and reception of the antenna, to correct for the homogenities. So we have to deal with the fact that the hardware, the coils, will not give us as much sensitivity, a flat sensitivity. So there are places where the signal emitted or perceived will be higher or lower. So we have to account for that. We want to be giving numbers in hertz for relaxation. And so we need to scale things. It's not just about having contrast. Gray matter is darker than white matter. We want to have a number that has a meaning. You know, if it should be so many hertz, it should be so many hertz precisely, or as precisely as possible. And as a consequence, because we start with a bunch of images, to put it bluntly, raw data are messy. I mean, you have per subject, a simple data set would be 20 or so high resolution images, and in the 40 to 50 smaller, lighter field maps fields. So that's what the scanner is spitting. And so for the MR physicist, that's the acquisition. The rest is post-processing. For the engineer, this is where the processing and the hard work starts, is making sense of all those data. So that's actually the cool thing is the code is open. There is Martina's, there is an example data set available. So this is from the example data set. So if you look at what you get 12 folders, each containing a bunch of images. And each folder has those images with a JSON file that contains some parameters. So the hard part is we need those tiny, well, those numbers, echo time, flip angles, for each and every image in order to make sense of them. And that can be complicated, as they are not always systematically saved in the DICOM header and the import export into conversion into Nifty. There were some innovative ways of storing the flip angles, as far as I remember. If you want the details, I can explain that. And just to mention that over the COVID period, we worked on brain imaging data structure extensions for qMRI. The idea is that we have conventional images, quantitative maps, but also group scan, and that includes the NPM protocol has been included in the description. And the idea is that now the images have a fixed or standardized way of being described in terms of parameters, which makes things a bit more palatable. So here you would have the data for one subject, that's the field maps, that's echo1, flip number 2 for the transmit V1 EPI volume, and that would be the anatomical images. And then, for example, you can now more explicitly recover, or at least we have recovered and written down in an explicit way the TR value, which is that's like 25 milliseconds. The echo time is 9.2 milliseconds with a flip angle of 6 degrees. So everything now is a bit more explicitly described in the data, which helped my life in terms of tool development. Yeah, and we work also on some tools to operate these conversions. No, that's the map creation. We also rely heavily on SPM machinery, and that's at 2 steps: spatial processing and the statistical analysis. Actually, the statistical analysis is outside of the hMRI Toolbox. We simply fall back on the standard SPM interface for GLM and inference. For the spatial processing, pretty much I was in charge of, or at least I revamped, I refactored some of the code. What we did is we didn't change anything in John's code. We just rearranged the GUI to be a bit more in line with the format of the data, that for each subject, we get some quantitative maps. So we knew in advance that we wanted to process the data in a specific way. So we just modified the GUI, but it's the same functions under the hood, except for 2 steps, which is the smoothing and the mask creation. The smoothing has been slightly tweaked because those maps, quantitative maps, if we smooth them with a Gaussian kernel, we'll be mixing signals that have a physical interpretation. So we'll be mixing the signal from white matter with the signal in the gray matter, and it doesn't make sense to mix them because they are 2 different. They are quantities that have a physical or biological interpretation. So mixing them is ruining that part. So there are some tissue specific smoothing that was proposed by John originally for Bogdan's paper. And then mask creation, I'll illustrate that. And for the statistics, we just do substandard univariate RF random effects analysis. Then I'll probably have a word with Tom and Ferhat about the risk of multiple GLMs, and I will elaborate a bit more about that. So the tissue-weighted smoothing, the idea is that we are taking the original map, but we smooth it either specifically for gray matter or for white matter. So we are this. So we use a Gaussian kernel, but we apply it on the weighted tissue, the weighted map by the tissue probability. And then we scale it with the Gaussian, the Gaussian smoothed tissue probability maps. And in the end, we get gray matter smoothed, for example, MT-SAT images, and white matter smoothed MT-SAT images. Those images, as you see, I call them like popcorn images because they sort of blown up gray matter, blown up white matter. And to make sense of them, typically we also rely on a gray matter mask or white matter mask that are not overlapping. So pretty much what we decide is that voxel is predominantly or should be considered as gray matter, and that voxel should be considered as white matter. And you would be analyzing, you would do your GLM for the gray matter and the white matter separately. And because we have actually 4 maps, you would do that for each and every map separately, R1, R2, PD, and MT. Hence, the potential issue of multiplying the number of GLMs that we are doing and the risk of false positives. Oh yeah, and that's the more technical things like in the GLM using float or integers will give you slightly different implicit mask, and I found that the hard way. I can again explain what I mean by that. So the ongoing things is we kept on working. The next release is planned for early October with a few new features. The features, one of the cooler things is the denoising tool. So there were a few publicly available tools written in Java. Yeah, a bit of something different. And these were interfaced in the hMRI Toolbox MATLAB GUI, through this Java MATLAB interface. And that's again the image doesn't make justice to the difference. But on the left, you have the original R2 map, and it's a bit of salt and pepper noise if you look at them closely. While on the right, it's the same map after a LCPCA denoising tool. And so we have denoised the original data before the model, and in the end, that's providing a less noisy map. One thing also, those maps, they are point estimates. So it was like, how much should we be relying on the value we're observing on each point? And therefore, Siawush worked on providing error maps. So now we've got the point estimate, but also sort of the deviation, the errors or the amplitude. So we could get a SNR per voxel at each and every location. And also that means that we could be, and there is a submodule that allows you to combine multiple measures, weighting things with the error level at each and every voxel. That's with Antoine and Martina, the quickie analysis, where this is about quality of the data. And that's more the statistical inference. If we know that some maps are noisier, i.e. less reliable, that's included in the covariance matrix of the residuals of the GLM. And so that's sort of down weighting those less reliable measures. And that that was shown in a paper by Antoine. That's overall improving the statistics and sort of whiten the residuals and the variability, the variance across all the subjects in the study. And finally, more IT, that's the homosedasticity of the residual noise distribution. That's improved. The package now is there is a standalone version on MATLAB. So it's compiled, it's MATLAB runtime, and it's also integrated into Neurodesk that was mentioned as well. Future stuff. Well, objectives, as Nick mentioned, they are physicists, wonderful. There are always plenty of ideas, new ways of acquiring data. Every time they change the sequence, we have to adapt the reconstruction methods, the tools and everything. So we are not going to be out of job anytime soon. Yeah, and so data curation is becoming also important, and that's the bit standard to be extended, stretched, so that's something to be discussed. Improved processing, so in spatial, that's for John, those maps, they contain more than just tissue shapes. So multi-channel segmentation, how many Gaussians per tissue class, these are all questions that I've been pondering about. Warping, we're using Dartel, we should probably use Shoot, or multi-brain that you will be presenting tomorrow. That's good, we didn't move to Shoot. You can the smoothing, that's as I mentioned, there are other ways of doing tissue weighted. There's the teaspoon, but also is it really relevant? And yeah, the statistical inference, that's the issue of 8 GLMs. That means 8 inference per contrast. So you want to test difference between two groups, well, you do it 8 times. 2 tissue maps, 4 maps per, 2 tissue classes, 4 maps per tissue class. So there is a risk of multiple comparison and a lack of sensitivity. And so recently I've started using a tool by Ferrat, the MSPM, and we were quite happy with new or previously unseen voxels in regions in our results. So possibly increased sensitivity. But that's something we would like potentially include in the hMRI toolbox because it makes sense. We have a single inference instead per tissue class instead of 4. Conclusions, well, we live in a framework where everyone has his own constraints and interests, so let's make the best out of it. And thank you for your attentions and all those who provided slides and images. Thank you.